Good afternoon. What a great turnout. Ever since I started introducing the Colloquium speakers, the participation rate has soared. Well, it's an honor and a pleasure to introduce Professor David Griffith as today's Colloquium speaker. David received his BA in 1964 and Ph.D. in 1970 from Harvard University, that famous school in Cambridge, Massachusetts, commonly known as the Stanford of the East. Although his Ph.D. was in elementary particle theory, his recent research has been in electrodynamics and quantum mechanics. I learned last night that when Ed Purcell taught electrodynamics at Harvard in the 1960s, David was his teaching assistant. In addition to his technical papers, Professor Griffith is well known worldwide among physics and engineering faculty and students as the author of 4 highly regarded books. Introduction to Electrodynamics, now in its 4th edition, Introduction to Elementary Particles, 2nd edition was published in 2008, Introduction to Quantum Mechanics, again 2nd edition was published in 2005, and his latest book is Revolutions in 20th Century Physics, published last year by Cambridge University Press. Griffith is a consulting editor of the American Journal of Physics and a fellow of the American Physical Society. In 1997, he was awarded the Millikan Medal by the American Association of Physics Teachers. He has spent sabbaticals at SLAC, Lawrence Berkeley Laboratory, and UC Berkeley. In the spring of 2007, he was visiting professor of physics at Stanford. I'm sure you have all heard of hidden agenda and hidden treasures and hidden assets, but hidden momentum? Well, that's the title of David's presentation today. Without further ado, allow me to invite Professor Griffith to the podium.
Thank you. Actually, the title of the talk was intended to provoke and irritate Masood, but so we'll see if I succeed. I'm going to tell you an interesting story from classical electrodynamics. Can you hear me okay? I hate these things, and I sound really echoey and weird, but apparently they need it for recording purposes anyhow, so we'll make do with it. According to classical electrodynamics, as you well know, electric and magnetic fields carry energy, momentum, and also, for that matter, angular momentum. The momentum density in an electric field E and a magnetic field B is given by the famous formula that's actually very closely related to the pointing vector, except that it's an epsilon naught instead of 1 over mu naught. But this is the momentum per unit volume stored in an electric field E and a magnetic field B. By the way, since I assume that most of you are students of optics, I should tell you right at the start that I'm talking about electrodynamics in vacuum, not electrodynamics inside matter. So E and B, don't worry about whether you think that should have been a D or an H or something. That would be relevant if we were talking about electrodynamics in matter, but we are not. This thing sounds like it's echoing and buzzing, isn't it not? Not too bad for you? Okay, so there's the momentum per unit volume, E cross B. And the classic application of this, of course, is to momentum transported by a light wave, or in general, electromagnetic wave. Here's the classic cartoon of an electromagnetic wave across electric and magnetic field. If you take your right hand, E cross B points to the right. Which is the same as the direction of propagation for this field. So the electromagnetic wave carries momentum which we could calculate from this formula. And how do I know that that's true? Well, I might let the light hit an absorber, like the brick wall over here, and when it gets absorbed, that momentum gets dumped into the brick wall in the form of the pressure of light. So the manifestation of momentum transported by electromagnetic wave is the pressure of light when the electromagnetic wave is absorbed. However, even purely static electric and magnetic fields can also harbor momentum. If you think about it, if this formula is correct, then I could have purely static electric and magnetic fields, and as long as they're not parallel to one another, then there's going to be momentum stored in those fields, and that seems a little bit more peculiar. The electromagnetic wave is perfectly natural that it should carry momentum, but even purely static electromagnetic fields can harbor momentum according to classical electrodynamics. And here is maybe the simplest possible example of that. I've got simply a parallel plate capacitor here, positively charged plate and a negatively charged plate. So they're producing a nice uniform electric field that points from the positive toward the negative there in the region between the plates, and a zero field in the exterior region. And now suppose that I turn on a magnetic field that points in the x direction here. Then I have E cross B. E cross B, if you use the right hand, points to the right. So they tell me that, that this system, a purely static capacitor, charged capacitor, in the presence of a purely static magnetic field, nice uniform magnetic field, I suppose. And let's see, what is the total momentum in that capacitor, in the fields in the capacitor? Well, remember, it was epsilon naught times E cross B. E and B are perpendicular, so it's just a magnitude of E times B. That's the momentum density, and I multiply it by the volume, the area of the top plate, I should have indicated that on there, times the separation distance D, should have indicated that too. But this is simply the volume of the region between the parallel plates where the electric field resides. So what this is telling me is that if you take a static charged capacitor and turn on a nice uniform magnetic field pointing perpendicular to it, that arrangement contains momentum in the fields, and moreover that momentum points in the least likely direction of all, the y direction in this figure. The electric field is upward, the magnetic field is coming out of the page, the momentum is pointing to the right, and yet nothing at all is moving. Is that weird? I think it is, but that's what the laws of electrodynamics suggest. That purely static configuration harbors momentum that's stored in the fields. How would I convince a beginning physics student that there really is momentum stored in those fields? Well, the obvious way is to turn off one or the other of the fields. That would eliminate the momentum stored in the fields. By conservation of momentum, it's got to go somewhere. Where is it going to go? Well, it must get dumped into the capacitor. So what I'm saying is that if this is really true, that there's momentum stored in the electromagnetic fields, then if I turn off the one, either E or the other, B, this capacitor ought to get a jolt to the right, a kick to the right in the amount, the impulse, which resulted in its momentum to the right, should be given exactly by that formula there. So I'm going to convince you as a student of physics that there really is momentum stored in the fields by getting that field to come out and show its face as momentum of the capacitor. So first of all, let's imagine that we turn off the electric field. How would we do that? One thing you might do is connect a little wire between the positive plate and the negative plate and let the charge drain off. So a current would then be flowing up that little wire, and I imagine that it flows fairly slowly, so put a lot of resistance into that wire so that I don't need to worry about radiation or anything like that. It's a quasi-static process, and the But now I have current flowing in the upward direction in the presence of a magnetic field B pointing out of the board. That means that according to the Lorentz force law, there's going to be a force on that wire. In fact, what is the force? The Lorentz force law is I times L, the length of the wire, times B, I dl cross B in differential form. So I is going upward, I dl is also going upward, crossed into B, would be a force to the right. Exactly right. There's going to be a force on this little wire that gets transmitted then to the capacitor, and it's going to give this thing a kick to the right. Is it exactly the right amount? Well, I got to calculate the impulse delivered by that force. So I, that's script I, is impulse is the integral of force times time, would be, let's see, I dl. The dl is just d, the length of the wire, cross B. So dl, B, and here's the I, the current flowing in that wire, the rate of change of the charge on the capacitor. Integrate that with respect to time, and it just gives you d times B times Q. So that's the impulse that's delivered to this capacitor as I discharge the plates. Now, of course, E, the field inside a parallel plate capacitor, is sigma over epsilon naught, so that's charge over area times epsilon naught. If I rewrite this then, replacing the Q by A epsilon naught E, then I get, instead of that Q, A epsilon naught E, there's the formula, epsilon naught E B A D Y hat. That's exactly the momentum that was originally stored in the fields in the capacitor. Are you convinced? So I could get that momentum to come out simply by discharging the capacitor. But I could do it another way. Also, I could turn off the magnetic field. If you turn off a magnetic field, that's a changing magnetic field. A changing magnetic field induces an electric field by Faraday's law. And again, I should... And the electric field then is going to exert a force on the top plate where it's negatively charged and on the bottom plate. In fact, B, remember, was coming out of the board in the x direction, so dB by dt is what Faraday's law is. dB is the the line integral of E dot dl is the rate of change of the flux through the loop. The flux is going around in this direction, so it looks like I've got a force to the left on the upper plate and a force to the right on the lower plate. But wait a minute, there's a minus sign in Faraday's law. Faraday's law says that let's do it in differential form. The curl of B is the curl of E is minus dB by dt. So actually, the electric field, the induced electric field, is circulating around in this direction, therefore pointing to the right. B was coming out of the board. dB by dt is therefore pointing into the board. The right-hand rule would say a field pointing around in that direction, as I just said, but actually there's a minus sign, so it's going around in this direction. Woo, did I finally get that right? Okay, there's an electric field and it's circulating around in this direction. On the top plate, there's a field to the left, but the charge is negative. That's a net force to the right. Yes. On the bottom plate, the electric field is pointing to the right, but down there the charge is positive. Again, it's a force to the right. So because of Faraday's law, then, I'm going to get a force to the right, and let's calculate exactly what here's Faraday's law. I should have had that slide up there before. And now what I need to do is calculate the force due to that on the upper plate and on the bottom plate. I know that the force is going to be to the right. I'm just trying to check that the amount is exactly right. The force on this little sliver there would be the electric field in the y direction times the charge on that sliver, which is sigma, the charge per unit area, times the length of the sliver times the width of the sliver. So that's W times dy. And that, if you care to, you could write it as sigma times W times E dot dl. That's the electric field on a sliver at the top. Of course, I need to integrate that over the entire length of the top, and then I need to integrate also over the bottom. So what does this give me? Sigma times E, sigma times W times the integral around the closed loop of E dot dl, but the integral around the closed loop of E dot dl is minus the rate of change of the flux. That's the area of that loop, d times the length, the width times the length of that loop, w times d, times, wait a minute. No, the W came from here. It's D times L is the area of this loop, the Amperian loop here, and then dB by dt, the rate of change of the magnetic field, and that's then the impulse is the integral of f dt again, and I've just put in these quantities, integrated up, and you get again dBq times y. That's the somewhat simpler way of writing the net impulse delivered to the capacitor, and which is the same. What is the same thing? The momentum that was originally stored in the magnetic field. How did I make that so horribly complicated? Do you understand what I tried to say? There was originally momentum in the region between the plates of the parallel capacitor stored in the electric and magnetic fields. I turned off the electric field, then by Lorentz force law acting on the connecting wire, I got a jolt to the right and the impulse was exactly the same as the momentum originally stored in the field. If instead I turned off the magnetic field, then Faraday's law says that that induces an electric field. I calculate the force, electric force on the top plate and the bottom plate, and I get exactly the same impulse again to the right. So no matter whether you turn off the electric field by discharging the plates, or you turn off the magnetic field by maybe controlling the electromagnetic magnet that was setting it up in the first place, in either case, the momentum originally stored in the fields is extracted in the form of physical momentum of the capacitor plates. They get a kick to the right. So there's a summary. Momentum originally stored in the fields, momentum delivered to the capacitor as you discharge it, momentum delivered to the capacitor as you turn off the magnetic field, all the same. Beautiful. Are you convinced now that the electromagnetic fields really, honest to God, carry momentum? I convince you because I can get that momentum out by turning off the electric field or the magnetic field. Beautiful. This is probably the right time to confess that problem is in the third edition of my electrodynamics book. And I was very proud of it. Not that I invented it. This is an obvious example, and it's been discussed quite a bit in the literature over the years as a very simple example of momentum stored in static electromagnetic fields. Sad to say, almost everything I've told you is false. And today's lecture is going to be the saga of the demolition and then the reconstruction of this beautiful problem that was so simple and convinced you all of the reality of momentum stored in electromagnetic fields. The story begins when I got an email from a fellow by the name of David Babson, a student at North Carolina State University. He wrote me an email saying that he thought that I had actually done an incorrect calculation here in calculating the force when you turn off the magnetic field. You'll notice I tried to do this quickly so that you wouldn't notice, but actually when I was calculating the force, what I really wanted was, remember, the changing magnetic field induces an electric field, and that electric field exerts a force on the upper plate and on the lower plate, right? I should have integrated across the upper plate, and then I should have integrated across the bottom plate to get the total force. But that's not quite what I did. In order to exploit Faraday's law, which tells me about the integral around a closed loop of E dot dl, I secretly slipped in the left-hand side and the right-hand side. So I had actually integrated around the wrong path, or I had thrown in a couple of extra terms. Well, when Babson wrote me this email, I wrote him back a patronizing little email saying that, of course, I imagine that the parallel plates were very close together, as we always, for parallel plate capacitor, you're assuming that the plates are very close together so that the field is nice and uniform. And because they're very close together, that D is negligible, and therefore the contribution of the two ends would be insignificant, and that's what I was obviously assuming. And he wrote back very patiently and said, no, actually, I think that doesn't solve the problem, that the contribution from the two ends is not insignificant, even if the plates are very close together. And again, I wrote back to him and said, no, do the calculation. You'll find out that I'm right. But he wrote back and said, well, let's do a specific example, an example where I actually know what the magnetic field is, and therefore what the induced electric field is, and I can control every part of the argument, and we'll find out whether those ends actually contribute or not. His proposal was the obvious one. Why don't we stick this capacitor into a nice uniform field? How do you get a uniform magnetic field? Well, a long solenoid is the classic way of doing that. So let's imagine that really the system is this. There's my parallel plate capacitor, and it's inside a long solenoid that's got, of course, a current running around like this, producing a nice uniform magnetic field. And now as I turn off that magnetic field, I can calculate from Faraday's law exactly, because of the symmetry of the problem, the symmetry of this nice circular cylinder, I can calculate exactly what the electric field is. Namely, if I take an Amperian loop like suggested on the left-hand end, E points circularly around that loop. E times the line integral of E dot dl is E times 2 pi r, the circumference of the loop, and that's minus the rate of change of the flux through the loop. That would be the area of the loop, pi r squared, times dB by dt. The rate of change of the magnetic field. And from this, if you divide through by 2 pi r, you got E is equal to r over 2 times dB by dt, and it points in the phi hat direction, if that's the azimuthal direction indicated here. Well, that means that E dot dl, whatever dl is, I'm going to be applying this to, remember, a loop, a rectangular loop that goes around there in the capacitor. But first of all, let's just write down what E dot dl is as r over 2 dB by dt. Phi hat, I've written that out now in terms of its Cartesian components, y hat and z hat. If you don't remember the formula, neither do I. Look it up in the back cover of your favorite E&M book. There's phi hat, and now I dot it into dl, and that would just be in general dx x hat and dy y hat and dz z hat. And then I combine take the dot product here. I've got in the y component minus sine phi dy, and there was another minus out in front, so it's r sine phi, and likewise the z terms become r cosine phi dz. And r sine phi, if you think about it, is nothing but z, and r cosine phi is nothing but y. So really, reduced down to simplest terms, there's E dot dl. Now, what am I going to do? I'm going to integrate along the plates. There, the dy integrates to the entire length of the plate, but dz is quite small. That's half the separation distance, d over 2 actually. So that term has a small z and a large dy, integrated dy. On the other hand, the two ends that Babson had pointed out, I had integrated over, but I really shouldn't have y, which is relatively large out there at the edge of the plate, and dz, which is very small. So small, large, large, small, the two terms actually are exactly equal. What I should have done is integrated just along the top part where I get the z dy term, and just along the bottom part where I get again the z dy term, but I shouldn't have included the integral up the two sides where I pick up the y dz term. So suppose that I did this correctly now, integrating only over the top and the bottom, plugging in this formula, I get exactly 1/2 what I had got before. In other words, Babson was exactly right that the top plate and the bottom plate contribute half to the total line integral, and the two ends, which I shouldn't have included in the calculation, give the other half. So the answer should have been 1/2 what I got before, because I had inadvertently included the two ends. That make sense? So back to my beautiful chart of the consistency of this whole thing. The momentum delivered to the capacitor as B decreases shouldn't have been BQ dy. Should have been half that. That's the correct calculation. Meanwhile, I had heard from a guy at Princeton, Kirk McDonald, who had done a careful calculation of the momentum initially stored in the fields, and he reported that this answer was incorrect. How can that possibly be? Remember how I got it? The E was uniform, the B was uniform, and I just multiplied by the volume between the plates. But McDonald points out that any actual parallel plate capacitor has a fringing field around the outside. You familiar with that? So here are the two plates, and the field is strong in the intermediate region and relatively uniform, but when you come to the edges, it weakens, and then there's this fringing field on the outside, which we normally ignore for the same reason as before, that the parallel bring the plates very close together, then the fringing region is insignificant. But it does mean that my calculation was suspect, and McDonald, by a very clever method, showed that the actual answer is not that, but 1/2 that, because of the role of the fringing field. I'll sketch how McDonald argued this. Go back to the formula for momentum in electromagnetic fields is E cross B. Because that is quadratic, or rather bilinear in the two fields, it does not satisfy the superposition principle. In other words, the momentum of the combination of two, the superposition of two configurations, is not the sum of the momentum of the one plus the momentum of the other. You would have E1 plus E2 crossed into B1 plus B2, and that's going to give a couple of cross terms in there also. However, so this is probably a familiar problem to you. If you're calculating energy or momentum or angular momentum in electromagnetic systems, watch out, because the superposition principle does not apply to those. It applies to the fields and to the potentials, but not to energy and momentum. However, suppose that E was actually uniform over the entire region where there's any B. In other words, the entire region where I'm planning to integrate. Then the result, integrating over this, would obey the superposition principle in the in the non-constant variable there. Did that make sense? Or vice versa. If the magnetic field was constant over the entire relevant region, then it would be linear in E and would satisfy the superposition principle in E. And I happen to have now exactly a situation like that. The magnetic field was uniform. The electric field, McDonald points out, is not uniform because of the fringing field, but the magnetic field by construction was uniform. So the the momentum does obey the superposition principle in E. What does that tell me? It tells me that if in this particular instance, if I knew the momentum stored in the field of a single electric dipole, positive charge down here and negative charge up here, if I knew the formula for the momentum stored in a single electric dipole in the presence of a uniform magnetic field, I could immediately generalize that to any collection of dipoles. And if you think about it, a parallel plate capacitor is, in a sense, nothing but a whole lot of electric dipoles, negative charge at one end and positive charge at the other. So all I need to do is figure out what the momentum stored in an electric dipole in a uniform magnetic field is, and then I can immediately apply that to the actual configuration. So here, and here I've listed, these are well-known formulas for the momentum in a magnetic dipole in the presence of a uniform electric field. It happens to be 1 over c squared times E cross M. And electric dipole in a uniform magnetic field is 1/2, that's weird, it's 1/2 this time, times B cross P. But those are formulas that you can easily calculate. Just write down the field of a magnetic dipole or the field of an electric dipole, as the case may be, and do the integral, and this is how it comes out. So in particular, for an electric dipole in a uniform magnetic field is given by this formula, 1/2 B cross P. And therefore, by my superposition argument, it's also the case for any combination of electric dipoles, such as the parallel plate capacitor. So for the parallel plate capacitor, what I have, the total electromagnetic momentum is 1/2 B cross P, where P is nothing but the dipole moment, electric dipole moment of the capacitor. What's that? Well, it's the charge on the plate, Q, times the separation distance, D. So from that, I can immediately calculate what the true electromagnetic momentum for the parallel plate capacitor in a uniform field is. It's not BQD, but 1/2 B times QD. So McDonald shows that that is incorrect. Should have been 1/2. Now my beautiful example is completely corrupted. Two of these are consistent, although they're not what one by naive calculation thought they should have been. It turns out what I had advertised as the simplest possible example is turning out to be actually not at all a simple example. Both of those naive calculations are off by a factor of 1/2. But meanwhile, this one just sits there, nothing happens to that. Well, as a matter of fact, something does happen to that, as you'll see at the end. So there's the destruction of my beautiful example, but this started me thinking what I should have known right at the beginning, that all of this is complete nonsense because of a general theorem. A general theorem in relativistic field theory is a more general even than electrodynamics, that says, I call it the center of energy theorem. If the center of energy of a system is at rest, what's center of energy? Well, it's the relativistic generalization of center of mass, but in relativity, all forms of energy divided by c squared contribute, not just the rest energy. So it's actually the center of energy. If the center of energy of a system of a closed system. It's got to be confined, not one of these things that goes off to infinity like infinite parallel plates or infinite wires or something like that, but a closed system. If the center of energy of a closed system is at rest, then its total momentum is zero. Very powerful general theorem. So what I had told you at the very beginning, that parallel plate capacitor in a uniform magnetic field, the total momentum of that is not 1/2 BQ times dy. Still less is it BQ times d times y hat. It is zero, period. It's got to be zero by the general theorem. Somewhere or other, there must be some other momentum that compensates for the electromagnetic momentum that we have now correctly calculated here, the 1/2 BQ d times y. There's got to be some other form of momentum in this system. It goes by the name of hidden momentum because it's not associated with, it's hidden in the sense that it's not associated with motion of the object as a whole. But it is perfectly genuine momentum stored in that system. So I'm going to do a little diversion now and show you in the simplest possible context what hidden momentum is and where it comes from, and then we'll come back and see where the hidden momentum was in that in the parallel plate capacitor problem. So this is a different configuration. I call it the Calkin model for hidden momentum because that's where I first heard about it, first encountered it in a paper by Calkin, although I think it goes back to Penfield and House, actually, a book by two guys at MIT somewhat earlier. But here's the configuration. Suppose that I have a rectangular current loop here, and this just is carrying a uniform, a constant current around this loop. And I'm going to imagine for the moment that the current is just a bunch of, can we make them positive charges? I know electrons are negative, but that's irritating. They're just positive charges, and they float around that loop. They're not interacting with each other, and you're going to tell me that's not a realistic model for a current-carrying wire, and I couldn't agree with you more. We can dress this up, and it's been done to make this model more realistic, but it doesn't change anything about the essence of the problem. So allow me to use this model. I've just got these little ping pong balls, and they're all carrying positive charge, and they go around that loop. But now I put the whole thing in the context of an electric field that's pointing in the upward direction. What's that going to do? On the left-hand side, it's going to take these positive charges and speed them up because they're going in the same direction as the electric field. So they're going faster along the top part of the wire, and on the right-hand side, they slow down because they're going opposite direction to the field. And yet I say that you can't quarrel with this. I'm telling you, this is the model, that the current is constant all the way around. No charges piling up. We've waited for a steady state to emerge where no charge is piling up anywhere. If the charges are moving faster in the top segment than in the bottom segment, then there must be more of them in the bottom segment than in the top segment so that they would compensate, and so that the total current would be the same all the way around the loop. You got it? So that picture is not unreasonable. In the top segment, the charges are flowing faster, but there are fewer of them, and in the bottom, they're flowing slower, and there are more of them. And you say, maybe I see how this might have some momentum pointing to the right, because those charges up there are moving faster than the ones down here. Not so fast. The ones down here, the more of them. And those two effects actually exactly cancel each other. At least they seem to. So let's calculate what the current is at any point in the top segment of this loop. Current is charge per unit length, lambda times the velocity. Charge per unit length would be Q, the charge of each one, times n sub t, that's the total number of charges in the top segment, and divide that by L to make it the charge per unit length. So this is nothing but lambda, the charge per unit length in the top segment, times the velocity is the current in the top segment. And of course in the bottom segment is lambda down there, Q times n, the number that there are in the bottom segment, times over the length there, times the velocity of the bottom segment. And because I say that the current is the same all the way around, this tells me that NT times VT is the same as NB times VB, and it's I times L over Q. So the two are the same. Suppose that I calculate now what the momentum, the net momentum in this system is, the momentum to the right of the top ones and the momentum to the left of the bottom ones. Of course, the momenta of the ones in the sides are going to cancel. But classically, the momentum is mass times velocity. So what's the total momentum in the top? It would be the mass of each one, each ping pong ball, times the number that there are up there, times the velocity of the particles in the top segment. In the bottom segment, on the other hand, I would have, going the other direction, the mass of each one times the number there are down there times the velocity down there. But that is m times NTVT, which is IL over Q, minus m times IL over Q again is 0. Pretty much what you would have expected, isn't it? That the net momentum is 0. The net momentum to the right is 0 in this configuration because although the top ones are moving faster, there are fewer of them. Make sense? But I did that calculation classically. I used the formula, momentum is mass times velocity. That's not quite right. What's the relativistic formula for momentum? And you say, come on. Charges flowing in a current-carrying wire, relativity doesn't have anything to do with that, does it? Well, in this case, it does. I'm sorry. The relativistic momentum is gamma times mv, so I should have had a factor of gamma for each of those terms, and gamma is larger in the top segment. You know what I mean by gamma, 1 over square root 1 minus v squared over c squared, the relativistic factor gamma. Gamma is larger in the top one because velocity is larger there, so that throws its weight in favor of the top ones, and I get actually a net momentum toward the right because the top segment wins. Not because the number and the velocity, but because of that factor gamma. It's MIL over Q times the difference of the two gammas. The gamma at the top and the gamma at the bottom. Well, why are they different? They're different because the electric field accelerated the charges up here. Could I figure out, in fact, from that, what the difference of the two gammas is? Well, the energy, relativistic energy, is gamma mc squared. So the difference between the energy of a particle up there, gamma mc squared at the top, and one down here, gamma mc squared, the difference of those two energies is the work done by the electric field in driving this charge up the left-hand side. What is the work it did? The electric field times the force, the charge on the Q times E, did I say that right? Is Q times E, the force, times the distance, W. So Q times E times W is mc squared gamma top minus mc squared gamma bottom, divide off by the mc squared, and I got a formula for gamma top minus gamma bottom in terms of the electric field and the electric charge. So if I stuff that into here for the difference of the two gammas, I get that the relativistic momentum of this thing to the right is not 0, but ILEW over c squared. Interesting. I can rewrite that in terms of the magnetic dipole moment of this loop. What would that be? The current times the area. So the current I times the area, LW, is nothing but M, the magnetic dipole moment. I've got ME over c squared. And if you figure out the directions by the right-hand rule, the magnetic dipole moment is pointing into the page here. It turns out that the momentum in this system to the right is 1 over c squared times M cross E. I did that calculation very, very slowly and in detail because that's actually the essence of my talk. What is the hidden momentum in this? Maybe the simplest context for hidden momentum. It's 1 over c squared times the magnetic dipole moment crossed into E. That looks very electromagnetic, you know, a magnetic dipole moment and an electric field here. But notice that the momentum itself was not electromagnetic in nature at all. It got nothing to do with electrodynamics. It's got to do with particles that are moving faster in one segment of a loop than they are in another segment of loop. And if you calculate the momentum, the net momentum relativistically, you're going to get a non-zero answer. It's purely mechanical momentum, relativistic in nature, but mechanical in momentum. Now, I showed you before what the electromagnetic momentum stored in a magnetic dipole in a uniform electric field. You remember that one? Darn it. Here it is, the top one, the top formula here. The electromagnetic momentum for a magnetic dipole in a uniform electric field is 1 over c squared times E cross M. Can you remember that? M, E, and c squared. I've written this the other order instead of E cross M, M cross E, so there's a minus sign. It's exactly equal and opposite to the hidden momentum in that system. So here's a classic example of the hidden momentum, mechanical in nature, relativistic, exactly canceling the electromagnetic momentum coming from classical electrodynamics. So the total momentum of that system is 0. Which it's got to be because the center of energy is not moving. Got the picture? So there's one example. Now I want to come back to the parallel plate capacitor problem and see how this plays out in that case. Well, let's think about it. Where is the hidden momentum located? The hidden momentum is in the source of the magnetic field, actually the current carrying wire here, the thing that was producing the magnetic dipole moment. So a hidden momentum occurs in systems like this with internally moving parts, and it's located where the internally moving parts are doing their moving. The object as a whole, not moving anywhere, but the bits and pieces that go to make it up are moving, and the hidden momentum resides in those. Okay, how about the parallel plate capacitor in Babson's model, where, remember, the magnetic field was produced by this long solenoid. So I've got a solenoid and a parallel plate capacitor inside, and I know that there's momentum, electromagnetic momentum in the fields. It's 1/2, whatever, with Babson's correction there. But there's got to be hidden momentum that compensates for that, and it resides in the thing that's moving. What's moving? Not the capacitor. The charges in the cylinder. Well, wait a minute. This mechanism requires that they be in the presence of an electric field. Where's the electric field? Out where the cylinder is. Uh-oh, it's again the fringing field of the parallel plate capacitor. The only electric field in the problem is the external field of the parallel plate capacitor. So in order to run this argument for the parallel plate capacitor, I would have to know exactly what the fringing field is way out there where the current is in the cylinder. This is not an easy problem at all. As you probably know, fringing fields are a nightmare to calculate. I mean, you just simply can't do it in any realistic model. You could do it numerically, I suppose, but this is a nasty, nasty problem. I would have to figure out what the fringing fields of the parallel plate capacitor are out there at the location of the cylinder, and then I would have to do some complicated integration because different loops in the cylinder are in the presence of a completely different electric field. Not a nice problem. So I had a student, senior thesis student at that point, and I told her to figure it out. Rather, what I said was, let's contrive an example. The parallel plate capacitor inside a solenoid is out the window. There's no simplicity there at all. That's a monstrously difficult problem. We have subsequently done that one, but it's not something I would wish on anybody. So what is the simple case in which all of the fields are easy? We can calculate every field in sight and see this argument play out and manage to calculate the momentum in the fields originally, the hidden momentum in the system, and then turn off the electric field and turn off the magnetic field. Play exactly that same game that I did before, but this time do it right, recognizing that actually the total is going to be 0 always. So here's the model that we came up with. An electric dipole, an ideal electric dipole, in other words, a point electric dipole, take the separated electric and positive, negative and positive charges and squeeze them down to a single point. So I've got an electric dipole at the center. That's playing the role that the parallel plate capacitor did before. But it's a whole lot easier to work with because I know the fields of an electric dipole exactly. I don't have to say anything about fringing fields or anything. I know exactly what they are. Do I have them written down here? No, I do not. But you can look it up, what the electric field of a dipole is. And then I'm going to put it in the presence of a sphere, a concentric spherical shell that carries a uniform charge density sigma, and set that spinning about the x-axis. I don't know if you know this, but a uniformly charged spherical shell produces in the interior region a nice uniform magnetic field. Are you familiar with that fact? It's an interesting, not an easy problem, but an interesting example. So that produces a nice uniform magnetic field in the interior region. Of course, it also produces a field in the exterior region, and that's not too bad. In the here's the uniform field in the interior region, if omega is the angular velocity of rotation. Here's the field in the exterior region. It's the ordinary field of a magnetic dipole, whose dipole moment is given by that formula there. So look them up. Here's the field of the spinning sphere, inside and out. Look up what the electric field of the point dipole is. There's no distinction between inside and out. Now, you do have to include, by the way, the delta function or contact term in the field of the electric dipole. If you haven't encountered that, you would get the wrong answer in this calculation. But anyhow, I now control all of the fields, and I can calculate the integral of epsilon naught times E cross B to get the momentum stored in that field. Here it is, -1/2 P cross B, and no hanky-panky about missing fringing fields or anything like that. That simply is the answer. P cross B, let's see, P points in the Z direction, B comes out of the page, so P cross B is actually pointing to the right in the y direction here. And there's a minus sign, so in this case the electromagnetic momentum, the momentum stored in the fields, points to the left. Now I can do exactly the same job that I did before to calculate the hidden momentum in that system. Where is the hidden momentum? What's doing the moving? The spherical shell. So the spherical shell is in the presence of an electric field which I know, it's just a field of that dipole at the center. So I know the electric field. I run exactly the argument that Calkin did about the single loop, only here I have to integrate over the entire sphere, calculate the hidden momentum in that way, and you come out, no surprise, but comfortingly, 1/2 P cross B, exactly equal and opposite to the electromagnetic momentum. So far, so good. The actual momentum, total momentum in that system is 0, as it should be, because the center of energy is not moving. Now I want to play the rest of the game. Turn off the electric field. How would I do that? Connect a little wire between the positive and negative ends of that dipole and let it discharge, and then exactly the same mechanism as before. Because there's current flowing in the presence of a magnetic field, there will be a Lorentz force on that, and actually the calculation is just exactly the same as before. There it is. The impulse delivered to the dipole, because of the current flowing in the little wire discharging the electric dipole, I get minus P cross B. However, there's a second term, because now I have a changing electric field that electric dipole moment is changing with time. Changing electric field induces a magnetic field. That magnetic field exerts a force on the spinning sphere. Something that I had completely neglected before. You remember the middle term there? I said that there was a twist on that one also. The other two picked up a factor of 1/2 from Babson's argument and from McDonald's argument, but it seemed that there was no change in the impulse delivered when you discharge the parallel plate capacitor. That was actually incorrect, because when I discharged the capacitor, that was a changing electric field. Changing electric field induces a magnetic field. Magnetic field exerts a force on the current in the cylinder, in the solenoid on the outside. Not a nice thing to calculate in that case, but it's easy to calculate in this case, and you get that an impulse is also delivered not to the cylinder now, to the solenoid, but to the sphere. So an impulse is delivered in the backwards direction to the sphere. Awkwardly, however, it does not exactly cancel the impulse delivered to the dipole. So the dipole gets an impulse in one direction. The sphere gets a smaller impulse in the other direction. But the net momentum of the whole system now is not zero anymore. Not good. Because remember, the total momentum in the system originally, hidden plus electromagnetic, was zero. And yet, when I discharge the capacitor, discharge the dipole now, I get something that's not zero. Well, stick that on the back burner for a moment. And now let's turn off the magnetic field. How would I turn off the magnetic field in this context? Well, I guess I stick my foot on the spinning sphere, so somehow or other I slow the thing down, and I want to know, okay, changing this, now the current is changing, so the magnetic field is changing. Changing magnetic field induces an electric field. Electric field exerts a force on the dipole in the center. What is the impulse delivered to the dipole? Well, here it is. Take it from me. I'm not going to do the calculation, but again, we control all of the factors here, so it's a straightforward calculation. The impulse delivered to the dipole is -1/2 p cross b, and this time there is no compensating impulse delivered to the sphere. The sphere just, well, it's slowing down, but there is no linear impulse delivered to the sphere. So where do things stand at this point? Here's the calculation for the dipole and sphere problem, done now, I say, correctly, or rather almost correctly. Originally, there was electromagnetic momentum stored in the sphere, in the system. The hidden momentum exactly compensated for that. The total momentum was zero, as the general theorem said it had to be. Now I discharge the dipole. The dipole gets an impulse in one direction. The sphere gets an impulse in the other direction, but it's only half as big, so the total momentum is not zero. Bad news. If I slow down the sphere, the dipole gets a kick in one direction from the changing magnetic field inducing an electric field. The sphere gets no compensating impulse, and again, the total momentum is not zero. Okay, last element in this horrible story. Actually, I was scheduled to give a seminar on this at Williams College, and I had naively, when I agreed to do it, assumed that all of this was going to work out and that I would be able to present to them at the end this nice chart, and it would all be consistent. But a week before I was supposed to give the seminar, I had got to this point here, and it was not consistent. These two were simply not adding up. And then it occurred to me, what happened to the hidden momentum when I turned off the electric field or the magnetic field? when I turn off the, remember hidden momentum was mechanical, physical, mechanical momentum in the charges that are flowing around in the sphere in this case. What happens to that? Actually, it's probably easiest to think of this in the context of Calkin's model. What happens when I turn off the electric field, for example, so that the current equilibrates, the velocities equilibrate, the current's always the same here. These things knocking against the corners, the ones at the top lose some velocity, and ones down here speed up a little bit. Somehow or other in the mechanics of the equilibration of the velocities, that hidden momentum, which is present right at the moment, has got to disappear. And where does it go? It gets delivered purely mechanically. It's got nothing to do with electrodynamics again. It's mechanical momentum, and from bouncing off the four corners, it gets delivered to the structure, to the framework of this loop here. Or, in the case of the sphere, it gets delivered, the hidden momentum, which remember was stored in the sphere, gets delivered to that sphere. What I had neglected to do was add in the hidden momentum, which was 1/2 p cross b. That should have been, that was dumped into the sphere, should be added to this term here, should be added to this term here, because in both cases the hidden momentum was eliminated when you turned off the field, and therefore showed up in the sphere where it always was. So the momentum of this, if you add in the hidden momentum contribution, that was 1/2 p cross b, was exactly right to compensate for the fact that these didn't add up before and that this one had no balancing contribution. If you include the hidden momentum that got dumped into the sphere when you turned off the fields, the total momentum is 0 in both cases. So what actually happens if you set this up in the laboratory? The dipole discharges, the dipole gets an impulse in one direction, the sphere gets an impulse in the other direction, partly electromagnetic impulse and partly the hidden momentum, mechanical impulse delivered by the hidden momentum, but the two exactly cancel each other, and the net momentum of that system is 0. If you slow down the sphere, again the net momentum is equal to 0, although curiously it's just half as great in each case. So either way that you do it, the sphere flies off one direction, the dipole flies off in the other direction, but 0 total momentum in the system. Well, where are we? That's the reconstruction of my beautiful, simple example, which turns out to be not so beautiful and simple after all. I think that the hero, or maybe the villain of this story, is hidden momentum. So let me make a couple of comments about hidden momentum. First of all, it's mechanical in nature. I'm willing to bet not very much money that's also always true. I know of actually one model in which hidden momentum is something playing exactly the same role as hidden momentum is actually supplied by photons bouncing back and forth, which is to say it's electromagnetic in nature. But certainly in all of the standard examples of hidden momentum, it's purely mechanical in nature. I say it is intrinsically relativistic. You're never going to get hidden momentum in a system if you are using the non-relativistic formulas for momentum. It occurs in systems with internally moving parts, such as current loops, that was illustrated in the examples here. And it is not associated with motion of the center of energy, and that, I think, is why it came to be called by this actually very misleading term of hidden momentum. We call it, actually Shockley, who first identified it in the modern context at least, called it hidden momentum. It's a bad word because it makes it sound like it's mysterious. I've tried to emphasize to you that it's perfectly ordinary mechanical momentum, but it's momentum that's not associated with motion of the object as a whole, and therefore in some sense is hidden. Not mysterious hidden, but it's momentum that's not associated with overt motion of the object as a whole. I believe that's the end of my talk. It is. Thank you.